Hello and welcome back to Apt for You. In this particular video, we are going to discuss the problem bottom view of binary tree. We have already covered the problems of the left view, right view and top view. So in this particular problem, we are going to deal with the problem of the bottom view of the binary tree. So the problem is very simple. As usual, you are provided with a tree and you have the address to its root node, right? And what you have to do is basically you have to view the tree from the bottom. So you have to view the tree from the bottom and you have to say what are the nodes that will actually be visible, right? What are the nodes that will actually be visible? So it is clear, of course, that the nodes that will be visible in this case are nothing but node 1, from bottom will be node 6, node 4 and node 7, and of course node 5 also, right? These are the nodes that are actually visible when you watch the tree from the bottom, and you have to hence print the output as 6, 4, 7 and 5. So 6, 4, 7 and 5. This should be your output. Now the problem is, how do you deal with this particular challenge? So as usual, we are going to first of all create a number line, right, for ease of understanding. So this is my number line. Suppose, let me just point to them. So that makes the question much better. Great. So now you see, if I just consider this position of the nodes to be a point on the number line, then of course the root node will be at point 0. This will be at point +1, this is at point +2. Similarly, this is at point -1, right? So what happens? So now basically you can clearly see, like we have discussed in the problem of top view of the binary tree, that each node will be having a position on the number line that is denoted by h, variable h. So for this, h is equal to 0. Its left child will have position 1 less than the parent, so 0 minus 1, that is -1. Its right child will have position 1 more than the parent, that is nothing but h is equal to +1, right? Similarly, the right child of this node will have the value 1 more than the parent, that is nothing but h is equal to +2, +1 +2. The left child will have value 1 less than the root node, so h is equal to basically 1 minus 1, h is 0. Similarly, the left child of, that is this node, the address of this node will be 1 less than its parent, so 0 minus 1 minus 1. The address of this node will be 1 more than the parent, that is equal to parent address +1, so h equal to +1, right? So likewise, we have successfully assigned the value of h to each nodes. Now these are basically going to play a crucial role. Why? Because how we are going to solve it, you see, the output at any point on the number line, okay, the output at any point on the number line. For example, how many points we have? We have the point -1 point, let me take a lighter ink. So we have basically the points -1 here, point 0 here, point +1 here, point +2 here. Now we are going to traverse this tree from top to bottom in level order, okay, top to bottom. So we are going to use the approach or the algorithm for level order traversal. While we are traversing the tree from top to bottom, okay, what we are going to keep track? We are going to keep track of the nodes that are located at a specific position on the number line. For example, if you focus on this particular point -1, what are the nodes that are basically present on -1 on this position in the number line? So in the -1, you can see we have first of all node 2, and then we will have node 6. Similarly, if you point to position 0, on the position 0 on the number line, we have first node 1 and then node 4. Similarly, if you point to position 1, on position 1 in the number line, we have node 3 and then 7. Similarly, on the position number 2 on the number line, we have the node 5, right? So if you see the output very carefully, you will find out we have basically picked up the latest node in that number line while we are traversing from top to bottom. After the entire traversal is complete, what is the node that existed at the last, at each point, okay, which node you came across at that point at the end. For example, when I consider point -1, 6 is the last node in this number line, isn't it, at this point -1, because we have 1.2 and then followed by 6, bottom, somewhere at the bottom. Then we have point 0. In point 0 we have two nodes, 1 and 4. So initially when you are traversing from top to bottom, you will encounter node 1 first, and then later on at this point 0 you will find node 4. So the recent one will be picked up for the output. Similarly, if you consider point 1, you have node 3, and then you see when you come more bottom in the next level you will find node 7. So 7 will be picked up as the output from this point 1. Similarly, from point 2 you will get one node, okay, isn't it? Because from every point you are getting one node only, and which node? The node which lies in the lower levels. So from point 1 you pick 7, from 2 you will pick up only 5. So the output will be 6, 4, 7 and 5 as we are expecting. Now this thing will be dealt by level order traversal, that is traversing from top to bottom. How do you deal this? So this will basically be dealt by a map. So we will be using a map, and what will we do is, initially whenever we find the value of h, suppose initially value of h is 0, so we will do map of 0 with that data 1. Next time when you find h is equal to 0, again they will say map of 0 is equal to 4. So what will happen? This value will be replaced by the recent value in the next level. So obviously you got 4. Same thing happens for -1. Map of -1, you will get what? You will basically get 2. Next time when you reach at this -1, we will say map of -1 is equal to 6. So what will happen? This will be replaced by 6. So you can see likewise we are able to successfully keep track of the values in the lower level at particular point. So we are going to use two things: a level order traversal, okay, followed by using a map data structure. So let us quickly implement this particular algorithm. So having said that, let us just erase this particular portion, right? And now let us just quickly jump into the solution. So what we are going to have is basically we are going to use a output vector as usual, because the output will be stored in a vector of input integers. So vector integer output, right? So we have a vector integer of output. What happens is basically when this function bottom view is called, it will just say output.clear. Once output.clear is performed, it will call the function solve, right? The function solve is called. Now what are the parameters that we are going to pass in the function solve? So we are going to pass two things. First of all, the address of the root node, comma the initial value of h for the root node, that is 0, right? That's it. Once the when the function solve has successfully executed, or when the function solve has completed its execution successfully, all the update will be stored in the output vector. So finally we have to return the output vector. That's it. So it's time to design the function solve. So function solve we know is nothing but will be a void type function. What will it receive? It is receiving a root node, so node star root, and one integer it is receiving, that is h. Done. Now we are going to do what in the function solve? The function solve is going to deal with level order traversal. So what are the concepts of level order traversal? First thing we check is whether root is equal to null. So if root is equal to null, what we do? We just return it. Fine. Otherwise what do? We push the very first element into the queue, but before that you should have a queue. So let us declare a queue. Queue of what? Now we are going to create a queue of pairs. Why? I'll show you. We will be creating a queue of pair, and it will be basically a node address with integer, a node pointer with an integer. This is the structure of the queue. This is the type of the queue, okay, design of the queue. So we have declared a queue that will be holding data in pairs. Now what are the data that is going to hold? The address of the node along with the value of h. Fine. So initially we are going to push the root node. So queue dot push what in pairs? Root node address comma 0, or you can say h, right, because h is initially 0. So we are pushing it into the root node. That's it. Now what we are going to say? No, sorry. When you just push it, after successfully pushing the root node, we are going to say while queue is not empty, right? While our queue is not empty, what we are going to do? We are going to declare a pointer, which we generally do, that will point to my first element of the queue. So first element of the queue is nothing but queue dot front, and we will say dot first because the values are stored in pair. Okay, in the queue, as I've already explained in the top view problem, that the values are actually stored in pairs. Okay, because the queue I have declared here is in pairs, a node and an integer. So the first value will be a node address, second will be an integer value. So that is why, since current is going to store the address of a node, where will I find the address of the node? Queue dot front dot first. Similarly, I'll declare a value integer h, and it is going to store the value of queue dot front dot second, because the second value is the value of h, that is the point on the number line, okay, that we are assuming. Okay, fine. So having said that, now what we are going to do, we are just going to say that, okay, just pop the element from the queue. Once you have popped the element from the queue, now what happens, we just have to map that particular element. So I'll say map of h. Okay, so we have to declare a map also. So let us declare a map above. So we'll be saying map of integer comma integer. Let us keep it a name m. Anyway, so map of h. So what is the value of h? So initially my root is pointing to, isn't it? I'm doing a level order traversal. Initially I'm pointing to the root, this one. So first of all they will say map of 0 is equal to what? The value of that, so 1. So that will be nothing but root dot data is equal to not root data, current data, where current is pointing, right? Because I have updated the value of the first element of the queue in current, right? So current data, that's fine. And what you are going to do, since I am doing level order traversal, so if there are any element on the left, current left, if current left not equal to null, we are going to push them into the queue. So queue dot push what? Current left comma what? Now since I'm saying that since my queue is going to store data in pairs, so you have to push the data in pairs. So first of all the address of the left child, comma, what will be the value of h of the left child? 1 less than the parent. The value of parent is h, so h minus 1. That is what we do, isn't it? Same thing applies for right child. So if current right is not equal to null, means if there exists a right child, you are simply going to push the right child into the queue of pairs. So queue dot push into the pairs current right, comma, what will be the address of the right child? What will be the value of h for the right child? So 1 more than the parent. So parent value is h plus 1, isn't it? This is what we have discussed in the top view problem also. So that's it. So this is how the level order traversal will be performed, and every time the value of m, if it is value of h is repeated, then value of m will be replaced. For example, let us perform the level order traversal. Initially m of 0 is equal to 1, it's fine. Then what happens? Then we come across this node, and what is the value of h? Minus 1. So m of minus 1 will be equal to what? M of minus 1 will be equal to basically 2. That's fine. Next time you come here, m of 3 will be equal to what? Sorry, not 3, this plus 1, right? So m of plus 1 is equal to what? 3. Now next time what will happen, you'll come across this node which says m of 0 equal to 4. So m of 0 right now is 1, so it will be replaced by 4. Next time you come across this node, m of plus 2 is equal to 5. So m of 2 is equal to 5. Done. Now you come across this node, m of minus 1, because h is minus 1, is equal to 6. So this will be replaced by 6. Similarly this plus 1 will be replaced by 7. So what do you have now? 6, 4, 7, 5. Now when you print this map from top to beginning, so for that I'll be basically using here, I'm going to use an iterator. So for auto I, and let me just use an iterator. So for that particular reason I'm going to write, say, so I'm going to say for auto I is equal to m dot begin. Alright, and sorry, for auto I is equal to m dot begin, and I is not equal to m dot end. From beginning to end I'm going to traverse it, and I'm just going to say I plus plus, and meanwhile I'm going to push the value of the root, isn't it? So basically you see this is a map, the elements are going to be stored in pairs, and it is basically going to be sorted in the order of the keys. So that is why this is the keys I'm using. Okay, the value of h is being used as a key. So when it is getting stored in the sorted order of the keys, then definitely this will be first, this will be then followed by this, isn't it? Because you can see they are stored in the sorted order of the keys. So minus 1, 0, 1, and then 2. So I'm just traversing from beginning to end, and I'm just going to print the second value, right? So I'm just going to say output dot pushback, and I'm going to say I second. Okay, so wherever I is pointing, just push the second value of it. That is the root value that I have stored in this map, these values, right? This is what I want to push into my output vector. So successfully the output vector will be created and updated. So finally when this level order traversal ends, then you can basically print your output. So that's all from this particular algorithm, and considering the time complexity of this particular problem, obviously as usual we are performing level order traversal, visiting every node exactly once. So time complexity here will again be order of n. Space complexity is obviously not order of n because we are going to use this map, right? So let us, and also we are going to use queue, isn't it? So queue size also depends upon the, you know, the value of the element, isn't it? So queue size will be equal to 1 plus 2 into 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 number of nodes, so obviously order of n, right? So let us now quickly understand the problem by executing it. So if we just compile it, I'm expecting no errors, so I hope I have not made any mistake. So yes, the output is very fine, because you see 1, 3 and 2, if it is your tree 1, 3 and 2, if this is your tree, oh sorry, so 1, 3, 2 means like this, 1, 3 and 2, and if you're watching it from bottom, basically 3, 1 and 2 will be the output, and that is what we are getting, right? Submitting the code, exactly, that's all. So I hope this video was helpful. The problem has been successfully solved and executed, and I hope this was helpful. In case of any doubt, please feel free to put it out in the comment section. Just like, share and subscribe, and thank you.